Hello, my name is Neto, and I'm going to present my work to the VCCA conference on acoustic scene recognition applying to hearing aid devices. This is part of my research at University of São Paulo. My presentation is structured into the motivation section, and I'll do a quick theoretical background on the main concepts used in this work. Then I'll describe the database and preprocessing, the model architecture built, show the results, and conclusion and next steps. So, acoustic scene influences speech intelligibility and hearing comfort in hearing aid users. So we can use technologies such as machine learning models to improve the performance of hearing aids. And the goal here is to build a classifier that can identify acoustic scenes in an urban environment and further integrate it to a hearing aid to optimize the calibration of the hearing aid and deliver a better performance to the user. So starting with the background, theoretical background review, the features used to train our model are the MFCCs, the male frequency septural coefficients. And these are features that represent the short-term power spectrum of the sound. They are widely used in speech and audio classification tasks, and they use the MEL scale to build filter banks and apply to the signal. And they mimic how humans perceive pitch and loudness. The human hearing is more sensitive to low frequencies. It's nonlinear, and the MEL scale that the MFCCs makes use, they mimic and represent the human perception. So they're very useful to extract relevant features of audio signal. And also, its structure is very good to feed neural networks. The model chosen for this work are the convolutional neural networks, and the CNNs are basically neural networks that use the convolution operation instead of general matrix multiplication in at least one of their layers. So they're very specialized in process grid-like data like time series and images. And here we can see a representation of a CNN, a layer being applying the kernel into the input is the convolution operation, and the kernel it has a lower dimensionality from the inputs, and also we have fixed number of parameters in the kernel. So here we have a summary of the stages of a CNN. So we have the convolution layer, and then we apply the nonlinearity through the detection layer, and we have the last step, a pooling layer. So our data set, it's the TAU Urban Acoustic Scene dataset. It has 10-second audio segments, and they are classified in 3 classes: indoor, outdoor, and transportation. We have 40 hours of audio in approximately 13,000 samples, and we split our data to train our model in 3 sets: training, validation, and a test set that I extracted originally from the full validation set. And the preprocessing steps to the original data were to convert the data to mono and resample to 22,000 hertz. And then we extracted the MFCCs, deltas, and deltas, that these are the derivative and second derivative of MFCCs, but with a variance analysis of these features, I've decided to extract the deltas because they showed very low variance and they didn't improve the model performance. Here we can see the variance, and the deltas magnitude of variance are very low in comparison of variance of MFCCs and also the delta. So we designed our model to explore time frequency patterns, and it has 3 convolutional blocks with ReLU activation, batch normalization, max pooling, and dropout to improve regularization of the model. And at the final stage, we apply softmax to get the probabilities and consequently our labels. Here's a general diagram of the model architecture. Well, the accuracy chosen to evaluate the model was accuracy, and we get a validation accuracy of 89.3%, and in the test out of sample validation we got 85.61%. So the model presented good performance in general, being able to generalize well, being consistent between validation and test sets. And so here the training curves of the model, we can see that it improves its learning at each epoch, and there's a small gap between training and validation, but we find that this is normal, and specifically working with more than binary classification, it's common to get this gap. But with the confusion matrix, we can see that the performance of the algorithm was good. It has high level of accuracy between the classes. So in conclusion, we can see that the CNN-based model showed a good ability to classify acoustic scenes into our proposed categories. The MFCCs are good representations of the features, and our confusion matrix shows that our network learned relevant patterns from the data. So the next steps to our work is to apply the model to the real world and see how it performs in real-time processing data. And if we get good results in production, we can go to the integration of the model with the Tiresias project, hearing aid being developed at University of São Paulo. And these are the main references of my work, and I finish here, and thank you very much.